In this video, we're going to implement the posterior PDF for the two-parameter model, the straight line fitting model, namely this expression over here. And so the first thing we're going to do is simulate some data, some random data that follows a straight line, but with some noise. And then we're going to do the fitting. All right, so this is our synthetic data, and now we're going to make a plot of it. Let's try it out. Oops, something is wrong. Right here, my x is a row vector, and what I wanted it for it to be a column vector, so I'll just transpose it. There we go. So this is our synthetic data. Every time I run it, I get a new sample. All right, let's add the best fit line. So A here will be the design matrix, and it consists of a column of x's and a column of ones. And then this MATLAB backslash here for a non-square matrix will solve the normal equation. And then from this I can get my best fit parameter beta hat. And the order of these is the first one will be the slope and the second one will be the intercept. And the way we know is because the first column will multiply the first coefficient. And since we put in the first column the x's, then that means that the first parameter here, beta 1, is the slope. And beta hat multiplies the column of ones, and it's the intercept. So these are known as the least squares estimate, but they are also the most probable estimate based on the posterior probability that we derived over here. So let's add onto the graph a plot of the best fit line. Right next to comma. And now let's add some little stems to indicate the size of the errors. And when I said the errors, what I mean is the residual, the best fit model minus the observations. Oh, something is wrong. They're not from the best fit. I've put M and B. I don't know M and B, so I have to use M hat, the estimated one. M and B, this would be the deviations from the true straight line that the data was generated from. But I don't know what those true value is. So my stems, I want them to start from the red line, which is the estimated line fit. Let's construct the Bayesian posterior after marginalizing out sigma, the standard deviation of the noise. And what we need to pass in is, so here it's a multivariate PDF, and what we're going to pass in is a mesh of M and B points. And we're going to create the mesh and pass it to the posterior function. So I need M, B, these are going to be 2D meshes of slopes and intercepts on a rectangular grid. And we're going to evaluate at each point on the grid the posterior probability. These will be conditioned on the data. And let me show you how I will generate the M and the B. M, in space. Let's see what range I should put. So the true value is 2 and minus 2. Now, in reality, you don't know the true value, so there might be some trial and errors. You might use a range around the most probable. Maybe that's what I should do. So for M, I'll use M hat minus, well, I guess we can use an estimate of how broad the posterior will be based on an estimate for sigma. Sigma up here. So we can get a rough estimate of what sigma is from residuals from these. So let's compute that, and that'll give me a rough idea of how broad the posterior will be and how much area I need to do to integrate most of the posterior. And here we have to sum all the residuals, which is going to be y minus a star beta hat. So this is the residual. Oh, I need to square that. Maybe I should write it in the way I write it in the notes as that sandwich. First, the residuals. R is equal to y minus a. Okay, so we're going to pick 300 points, and we're going to go from m hat minus 5 times an estimate of this standard deviation on one side and 5 standard deviations on the other. That should be enough to capture almost all of the posterior probability. And similarly for B. No, that's not quite right here. This doesn't have the right units. Square root of S2 has the units of y, but m hat is a slope and it doesn't have the same units. So what I need to do is get a rough estimate of what the variance would be based on this kind of covariance structure. This is a rough estimate of the posterior covariance, but we'll see more of this later. All right, and then I do the mesh grid, and then I pass this to the posterior function. Okay, so the first thing we'll do is compute beta hat. We're trying to code up this expression over here. This is supposed to be beta minus beta hat. So maybe I can call this d beta. So that is this quantity, and it's evaluated for each and every point. So there's going to be a column of the difference between m and m hat and b hat. So the top component will be m minus m hat, b minus b hat at one point on my mesh, and then the next point shall be the different m minus m hat, b minus b hat, and the next one another m and b minus m hat and b hat, and so on. So we're going to have as many rows as parameters, one row for each, and as many columns as there are points in my 2D mesh of slopes and intercepts. And so we're going to evaluate the posterior at each and every point, and then we're going to integrate this probability to get the normalization. And what we want to compute is this a primed a times b minus b minus beta hat. So a transpose a, that is going to be a 2 by 2 matrix in this case. And that takes care of this part. And this will become, at the end, will be as many columns as there are points on my mesh. And then for each point, I'm going to multiply by beta minus beta hat. And then this, I'm going to sum over each row. So that's summing over the first column. That's the default for MATLAB, but I'll put a 1 to make it explicit. And so this sum will produce as many evaluations of this as there are points on my 2D mesh. Plus, and then I need this part. This one is easier to compute. And if I take the log of this expression, I'll have minus n/2, and I need to compute what n is. This is looking good. This is the log probability. And then I subtract off the maximum to prevent underflows. Okay, the reason we have to do that is because the log of the posterior probability is going to be a small number. Remember, if we have a big data set, then the probability of getting that exact specific data set, which is what the likelihood evaluates, is going to be an astronomically small numbers, because, you know, what's the chance if we measured 1,000 measurements that we get the precise value? Who could have predicted those 1,000 numbers, right? So they have a very small probability, and that means that when we evaluate the exponential of that logarithm will just get 0 in MATLAB. So instead, what we do is we subtract a constant from the logarithm, which is the maximum. That will make the maximum value equal to 0, the maximum of the log p after subtracting the maximum. And then when we exponentiate that, that will become a 1. So the posterior probability will have its peak value of 1 before normalization, and it'll drop off because every other point will be lower. And the parts that are really small, when you exponentiate, will get back 0. But at least there's going to be some place where the exponentiation is going to give numbers on the order of 1, which means that they will not be round truncated when MATLAB does its calculation. Okay, from this, now we want to compute the probability. And now to normalize it, what we have to do is integrate all the probability under the mesh. So that's why we need to make sure that we have a broad enough range of points that there's not much probability out in the tails, so that when we integrate, we can get an accurate estimate of the amount of probability to normalize. So dm db, that's the little rectangular area in parameter space m and b, and so I need to compute those. So
remember that m may vary, sorry, it goes the other way. M is the x-axis. So 2 minus m1, and then db.
So the mesh grid, this would be like if you put in x and y, you'll get x and y, the mesh of x's and the mesh of y's. So the x's vary along the second coordinate, and the y's vary along the first coordinate. That's why to do dm, I subtract the second point minus the first. It's going to be a regular mesh. And then summing gives me the total amount of probability, or the total amount of volume under that 2D curve, and then I use that c to divide it out from p to get a normalized PDF. And then over here, I'm going to create, to call this function, I'll first initialize p to be the same size as m. So I can do that, or b, just by multiplying it by m. And p is equal to posterior of m, b, y, and a. Let's see if that works. Probably not, but okay, so here's the problem. I think I need to put a parenthesis here first. Yes. So the dot star, try to evaluate d beta dot star with a prime to a. So what I need to do is first multiply a prime to a on d beta. It's all infinity, so it looks like I divided by 0. Yep. dm, db. db is 0. Why is db 0? Oh. Alright, so that looks good. This is the posterior, the log of the posterior probability. The actual probability is much more concentrated. If I take away the logarithm, you can see that you get a little ellipse of probability. Okay, so let's tidy up the code, make the plot, and then think about what we've just created. Okay, so this is the ellipse of posterior probability. So it says that the most probable value is here in the middle. Let's see if that works out correctly. M hat is 1.7, which is pretty much the middle of that peak. B hat is minus 1.9, is somewhere around here, which is the center. And then the width of this ellipse in this direction, if I integrate out m, I should get the posterior for b alone, and if I integrate out b, I'll get the posterior for m alone. So maybe we should have these marginalization and add the plots of the marginal. This is the joint probability. what's interesting is that this ellipse is tilted at this axis, which tells us that if I have an error in b that is too big, then my slope will be smaller. And you can see that by looking at the graph. If I make the intercept is down here, and if my intercept is too high, then I can't have the same slope because I'm going to miss all the data. So that means the slope has to be flatter to actually go through the data. So if I have my intercept is too high, then the slope has to be a little bit less to go through the cloud of data. And conversely, if the intercept is too low, then I have to have a steeper slope so that I'll go through the data. So if my intercept is down here, then my slope will be too high. So that's a negative correlation. A small intercept leads to a big slope, a big intercept leads to a small slope, and that's what this tilted negative direction between b and m means. That's saying that the posterior probability has a covariance between m and b estimates. And let's do the marginalized probability distribution for m and b and add them to the graph. Pm is equal to the sum, and here we need to sum, if we want the probability for m alone, we have to sum all the b values, all the columns. So that will be p comma star db. We want to have a probability with respect to m, so that's going to be distributed this way. So we're going to sum this way, and yeah, we're going to multiply by db, that's correct, db. And we're summing over the columns, that's the first index. And I need to create what db is p2 minus p1. And then to get pb, I'll do dm, which is m2 minus m1. And pb is equal to sum p star dm. And now to get this one, I need to sum over all the rows of the posterior mesh. So that is p star dm, and we're going to plot these marginal on the sides. Okay, and then I'll remove the title and I'll put the marginal posteriors plotted along the top and along the side edge. And so we can use this distribution to make inferences about b. And that averages over all the uncertainty in m. So this probability distribution reflects the uncertainty of b and takes into account the fact that we don't really know the correct value of the slope. And similarly, this probability distribution is a univariate distribution for the value of m. And since we've integrated over all the b's, the uncertainty in the b value, the value of b, is taken into account. So this axis here, this is probability density, and this is probability density. Maybe I could add those labels. Seems to work nicely. Okay, so that ends this lecture on estimating the joint posterior probability and the marginal posterior probabilities for m and b. And in this case, I've done all the integrations numerically, but in fact this student t-distribution, the integrations can be done analytically. It's just kind of tedious, and so I just did it all numerically over here. But the key is to make sure that we extend the range of m to be broad enough so that we get most of the probability, and that way our normalization will be correct and our PDFs will be right. I guess there's one thing that I want to show you before we go. Over here we got this kind of correlation, negative correlation between b and m, and that's just the property of the fact that the intercept is at the extreme left of the distribution of where my points are. If I had picked the range of x's to be on equal sides of x equals 0, then we wouldn't have this correlation between m and b, and they would be independent. So let me demonstrate that. So here my points go from 0 to 10, but if I change them from -5 to 5, just to shift in the definition of the axis for x, And now we get the kind of a circular, uncorrelated posterior PDF for B and M. So the correlations between the parameters have nothing to do with the data. They have everything to do with the model. And in particular, it has to do with this matrix A prime star A. The design matrix decides whether or not we'll have any correlations between our parameters in the posterior PDF. So if you have a good design matrix, you can have independent parameter estimates. If it's not so good, then you may have parameters that are very tightly correlated. And if you do a small change in one, it implies a big change in the other one. But you see here that A prime A has 0 off-diagonal elements. I guess I should look at the inverse of that, because that's the covariance. But the off-diagonal elements are essentially 0. C11, that's the covariance, that's the variance. But 1, 2 is 10 to the minus 17, so it's pretty much 0. And if I had my points, my intercept to be to the right of the interval, then try to guess at what kind of correlations we will get if I go from minus 10 to 0. Now we get a positive correlation. So if your error is too high, then your slope, if your intercept is too high, then your slope will have to be too high and to go through the data. And if your intercept is too low, then your slope will have to be too low to go through the data. And if we look at C, the estimate of C, then you see that you have very strong correlations. These off-diagonal elements are the covariances between the slope and the intercept, and they're very big. They're close to 1 in this case. All right, now that really does end this lecture.